This is a demonstration of Ustream Producer.
It's our pleasure to have here Professor Semenoff from University of British Columbia, who's speaking today. Just going to
This is a demonstration of Ustream Producer.
Yeah. Sorry about that. And for those who doesn't know, Professor Semenoff has had, I guess, a pretty successful career in field theory, especially field theory applied to condensed matter physics. He's been known for applications of, I guess, family of
This is a demonstration of Ustream Producer.
Physics, studies of anomalies, which is the breakage of classical symmetries in quantum field theory systems. And from one of the first works on graphene, I guess it can be safe to say that he was the first one that pointed the relationship of the relativistic structure behind the full structure of the Fermi surface of graphene.
This is a demonstration of Ustream Producer.
Worldwide, I guess we can just for the namesake mention the Majorana Prize, which pretty much sums up his recent interests, Majorana patents, and he's spending 1 month in the Institute of International Physics in Natal. So we met there, and he was kind enough to accept the invitation to come here and give a talk. Thank you, Professor Bruno.
This is a demonstration of Ustream Producer.
Very nice introduction, and it is indeed a great pleasure to be here and to have an opportunity to talk to you. What I'm going to talk about today is something which is a very long-term interest of mine, the subject of graphene. In fact, you might say I'm one of the people in the world who's worked on graphene the longest, which is sort of true, although
This is a demonstration
sort of
Ustream Producer.
I became more interested in it when it was discovered in the lab in the year 2004. And part of the reason for that interest I'm going to try to show you here today. What excites me about it. I'm a theorist, not an experimenter. So my take on graphene is from a theoretical point of view. What interesting theoretical issues are there, and one of the
Ustream Producer
is that theoretical issues can actually sometimes be tested experimentally, and so these are interesting times for people who think about these things. So what is graphene? Well, it's one of the common allotropes of carbon, four of which are drawn here. There's another one called diamond, which is a little different, made out of carbon. It's actually not a stable structure, whereas these are. So graphene is basically this thing where the little balls are carbon atoms.
This is a demonstration of Ustream Producer.
Our bonds, chemical bonds. This allotrope, which has been with us forever, is actually made out of pieces of graphene, and it's a substance called graphite. So graphite is the stuff that's in the lead of your pencil. If you do your calculations with a pencil, you use it on a daily basis. And in fact, it works so nicely as a pencil lead because this stuff, which tends to be black,
This is a demonstration of Ustream Producer.
Graphite has been around forever, of course, at least for a very long time. The other things, nanotubes and fullerenes, are actually things discovered in the late 20th century. In fact, fullerenes came from the 1980s, nanotubes 1990s, and then 2000, 2010 was graphene. Sort of interesting that The most complex was
This
found
is a
first, second
demonstration
most,
of Ustream
second,
producer.
and the simplest of the three structures was the latest one to be found, and that is more or less, as far as I know, just a historical accident. Here, just to show you that it's real, here is an electron microscope picture of this stuff. So an actual picture of the graphene lattice. So remembering back from the last page, the little
Demonstration
hexagons,
of
you can sort
Ustream
see them
producer.
here in the elementary cells of the lattice. And in fact, it's sort of interesting. In the real world, the real carbon atoms do look like these little balls. And the bonds between the atoms do look approximately like little sticks. So the stick figure wasn't so much of a pictorial after all. It in some way resembles the real stuff. One thing to notice from this picture, this is somewhat cleaned up graphene, taken, I should say, by the team electron microscope group in Berkeley.
This is a demonstration
It's a somewhat
of
cleaned up
Ustream
picture, but
producer.
you might notice it's actually already a pretty big piece, and it doesn't have any defects at all. It's a perfect piece. There's no lattice defects, and that's actually quite rare for lattices. A piece that big of just about anything will have a defect of some kind, or an impurity, or missing bond, missing site, and this piece of graphene just doesn't. And that's somewhat characteristic of graphene, that it comes even rather
This is a
crudely made.
demonstration
It
of
comes
Ustream
as quite a
producer.
clean substance, without much in the way of defects. The other thing you might notice is the color varies a little bit. The shade varies. And that's because graphene tends to come a little bit corrugated. It's not exactly a flat piece of carbon, but it has little hills. The size of the hills are between 10 and 100 lattice spacings, so they're macroscopic at the lattice level. And it's thought to have something to do with the
Demonstration of
stabilization
Ustream producer.
of the two-dimensional crystal. If you've read Landau and Lifshitz, they're in one of their famous volumes, there is a whole chapter explaining why two-dimensional crystals don't exist. For some reason, graphene avoids this. It does exist. Of course, it was first made on a substrate, which helps it exist. It's pasted onto something else, which stabilizes it. But it has been peeled off of the substrate, and it still
This is a
exists.
demonstration
But
of
it does
Ustream
have these
producer.
bumps, and I would say the theoretical description of the bumps, why they're there, how they help it exist, is still an open question. There are people who speculate there's some sort of a soliton of the phonon field. So phonons are supposed to shake this to pieces. If you just do rough calculations of what phonons will do to this lattice, it would shake it to pieces. And perhaps the bumps have something to do with stabilizing it.
This is a demonstration
See, that's
of
not really
Ustream
known, and in
producer.
fact, it's an open, interesting question. A great one for students to study, by the way. It's all simple stuff that pretty much anyone can figure out and work on. That's one of the beauties of this subject. And that goes experimentally as well as theoretically. So the graphene revolution really started when the stuff was discovered in the lab. It was known before as a theoretical model.
This is a
In fact, I worked
demonstration
on it,
of Ustream
20 years,
producer.
1984, 20 years before it was found in the lab. I was studying it as a kind of a theoretical model of something. But as a theoretical model, not realized in nature, was not so intensely interesting as once they discovered they could make it. This was done in Manchester by the group of Andre Geim. Of course, you know Stella was a postdoc there.
This is a demonstration
What
of
they
Ustream
did
producer.
was the following. They took some graphite, so that's the black stuff in these bottles. They rub it on a substrate, so they rub it on something. Then the legend at least goes that they take some Scotch tape and they paste it on and peel it off until the stuff is really thin that they rubbed on. And then after that, they could look at it with an optical microscope And they could actually identify
This is a
places
demonstration
where there
of
was a
Ustream
monolayer
producer.
of carbon on the substrate. And they could identify them simply because they had a different color, slightly different color, and they sort of could figure out which one was monolayer and which one was multiple layer. And so they look something like this. And surprisingly, this was the really big surprise, these pieces were big. They were like micron sizes. Just discovered by this crude mechanism, micron sizes, a reasonably macroscopic chunk.
This is a demonstration of Ustream producer.
This was an easy way to make a rather interesting material. I think we didn't realize it was interesting at the beginning. Actually, this might also be the stuff of legend, but legend has it that all of this happened during a Friday evening session at the lab. What they'd like to do is simply have a little party on Friday night and let the people who worked in the lab try out anything they want. And so this has nothing to do with what the lab was actually working on at the time. It was one of these Friday night tryout sessions where they decided to do this, just fooling around, and then they realized they had something interesting. And it took a little while. I think it was a group from the Ukraine who pointed out to them that this stuff could potentially be really interesting because it was a good conductor. It sort of had free fermions, free electrons floating around in it, but those electrons should obey a Dirac equation, and that actually makes it electronically a very interesting
Ustream
material.
producer.
The electronic properties are really quite fascinating. Just for that simple difference, instead of Schrodinger equation, it's a Dirac equation. Okay, so let's talk about the material a little bit more. So graphene is made out of carbon atoms that sit on this hexagonal lattice like this. A carbon atom has 4 valence electrons, 4 electrons in its outer shell.
This is a
In this
demonstration of
configuration,
Ustream
3 of the
producer.
electrons are used up in strong covalent bonds with the neighboring carbon atoms. The covalent bond is of carbon atoms is one of the strongest in nature. That makes this a rather strong material, and in effect the bond is rather stiff, so phonons don't play as much of a role in graphene as in other lattices. Of the 4 valence electrons,
Ustream producer.
the 4th one doesn't participate in these bonds, is left over. It has a different name in chemistry. These are sigma bonds, and this is called the pi electron. It's left over, more or less living by the carbon atom, and that extra electron is the one that will be responsible for all of the electronic properties, because it essentially is the one that will be able to move around. One thing to note is there is one of these extra electrons
Demonstration of
for every
Ustream
carbon
producer.
atom. So the charge neutral piece of graphene will have 1 electron per site of its lattice. That's the density of neutral graphene, and that will be important to us in a moment. How do you model graphene? Well, this is one of the other miracles, that it turns out to be rather well described by a really simple model.
This is a demonstration of Ustream producer.
If you have ever studied benzene, it's something similar because it has a hexagon. It just replaced the neighbors of the hexagon by hydrogens instead of carbons. Benzene is actually electronically quite a bit more complicated than graphene for some reason. The coherence of having all these hexagons side by side seems to simplify things a bit. So benzene is some complicated quantum ground state. The
This
sort
is a
of prototype of
demonstration of
resonating
Ustream
valence bond,
producer.
actually. Whereas graphene is rather simple. It's described pretty well by a tight binding model. So let me describe what the tight binding model is. The way you begin with a tight binding model is you assume that an electron is bound to each of the carbon atoms, so each site of this lattice. And then the dynamics of the model are basically just tunneling between neighboring sites. So there's some tunneling amplitude, which is called
Demonstration
T
of
in the
Ustream
Hamiltonian,
producer.
which basically gives the amplitude for tunneling, although it has energy units because it would be a Hamiltonian, but in a sense the amplitude for tunneling between neighboring sites. A nice description of this lattice, the hexagonal lattice isn't bipartite. That means it isn't, sorry, it is bipartite. It isn't a Bravais lattice. That means it isn't generated by two basis vectors. It's a little bit more complicated than that.
Of
In
Ustream
fact, it's useful to think of it as a combination of two triangular lattices. So those you can see as the black dots and the white dots in this diagram. The set of black dots is one triangular lattice. The set of white dots is the other triangular lattice. Those are called A and B sites. And then I've taken the wave function of the electron on B sites and labeled it B, and on A sites labeled it A. And all of the neighbors of an A site are B sites, and so this type binding model
This is a
couples
demonstration
A, B,
of
and A
Ustream
with some
producer.
amplitude here. The size of this amplitude is known. It's about 2.5 electron volts, which is quite characteristic of this sort of tight binding states. And also the lattice spacing is about 1.4 angstroms. Also a very characteristic atomic scale. Okay, this type.
Professor, the phase of T?
Pardon?
The phase of T? The T is a complex number.
The phase of T doesn't matter
This
if
is
it's
a
global,
demonstration
because you
of
could
Ustream
change the phase
producer.
of, say, all the B's, and that would change the phase of T. So it's just purely convention dependent. You could fix it to be real and positive if you want. This model was actually first written down for a lattice like this by Wallace in the 1940s. He was studying graphite, so he was using basically solving graphene as a starting point for solving
This is a
graphite, which is a
demonstration
little bit
of
more
Ustream
complicated.
producer.
Back planes with graphene. Graphite actually doesn't really have the properties of graphene. Somehow the planes are loosely stacked together, but they interact enough that it messes up a lot of the nice properties. So graphite, which was around forever, had some hint of the properties, but it didn't really have them. Anyway, this was studied by Wallace, who recognized that it had a linear spectrum, and then by me sometime in between, and by other people.
This
These
is a
people studied
demonstration
magnetic
of
fields and so
Ustream
on.
producer.
By me sometime later, we're kind of constructed the full Dirac equation for the electron in graphene. And one thing all these had in common is they all worked in Canada for some reason. I think it was the boundary condition. The first guy worked in Canada, and he was working on the heavy water nuclear reactor that used graphite rods for a moderator, and they needed to know the electronic properties of graphite for that. So that's what
This is a
motivated
demonstration
him.
of
And,
Ustream producer.
He later became a professor at McGill University and had some students. And I was not really in the line of students of these guys, but actually the director of the physics department where I worked at the time was one of the students of Wallace, and he actually told me about graphite and these sort of things when I came to him with some field theory problem, wanting to understand how to get relativistic fermions on the lattice.
This is a demonstration
He actually
of
said,
Ustream
well,
producer.
There's this peculiar thing in graphite, so there was a definite hint about what to do. Okay, so this model is nice. One nice thing about it is it's exceedingly easy to solve. So one of the great attractions of graphene is it's easy. Okay? Easy to make, easy to model, easy to solve the equations, and so you can do quite a few things. And so let me
This
walk
is a
you through the solution.
demonstration
So
of
here's the
Ustream
Hamiltonian
producer.
Bartite binding model. The Schrödinger equation that comes from it looks like this. It's just diffusion on this hexagonal lattice, right? The amplitude, the change in the quantum amplitude at an A site is just given by the hopping amplitude times the amplitude at B sites and vice versa. Those are nice linear difference, partial differential and difference equations. Of course, you solve them using the method of Fourier transform.
This is a
So there, plug in
demonstration
the Fourier
of Ustream
transform,
Producer.
and then what's left is you have to diagonalize a 2 by 2 Hamiltonian. And this is already looking Dirac-like, but it's not quite enough yet just to have it look like this. You need a little bit more. And that's because even on a square lattice, it would look like this, right? Hopping between neighbors, you could always write a Hamiltonian for that looks something like that. So there's a little bit more to it.
This is a demonstration
more,
of Ustream
what is more
Producer.
here is that these octagonal things are essentially complex functions. And what's going to happen is massless fermions are going to, relativistic ones are going to arise here when these things are zero, near the points where they're zero. There are two momenta in case, right, two components of the two-dimensional wave vector, and it's a complex function, so it's two real functions. So generically, you're looking for zeros of two
This is a
functions
demonstration
of
of
two
Ustream
variables.
Producer.
Those zeros will generically be at points. Okay, and that's exactly what happens. So you need this to be complex, and on the square lattice, the distance is actually real. So that's the difference here between the square lattice and graphene. Here it's complex. Okay, so one can figure out what the spectrum is. It's just the eigenvalues of this matrix, plus or minus. So they look like this. There's two bands, positive energy, negative energy band here.
This
Remember,
is a
the
demonstration
graphene lattice
of
should be half
Ustream
filled, so
Producer.
that negative energy band should be full. Positive energy band should be empty in the neutral sample. That means that states near the zeros of this thing are important because they're near where the electrons are filled up to in the neutral ground state. And as I just discussed, the zeros of this thing are gotten by finding a zero of two functions, this one, and they indeed do occur at points, which you can just find. And it's
This is a demonstration
easy now
of
to jump
Ustream
from
Producer.
formulas to pictures. So a graph of that energy spectrum looks something like this. All right, the horizontal plane here is the two dimensions. The hexagon that's written here is the Brillouin zone. That's basically momentum space for the lattice. And these are the negative energy states. These are the positive energy states. The Fermi level, right, when the system is neutral,
This is a
is right
demonstration
where this
of
plane is.
Ustream
All the
Producer.
negative energy states are filled, positive energy states are empty. The Fermi level cuts the spectrum at these discrete points here. Okay, these points aren't all independent. There are 6 of them drawn there. Actually, they're related by reciprocal lattice vectors. Only 2 of them are independent. So choose a black one and a white one. Those are what are called the K and K prime points. Near there, the spectrum looks linear.
This is a demonstration of
And,
Ustream Producer.
So that's where we're going to find the Dirac electron in a moment. So what do? Well, I'm a field theorist, particle physicist, so I don't really like this curly energy band. What do we do when we do lattice gauge theory, for example? Well, we chop it off. We put a cutoff and pretend that it's conical to that cutoff. You might ask, how high can that cutoff be? Well, I have to measure where it starts to curve in the previous picture. That's
This
how
is
high
a
it could be,
demonstration of
depending on how
Ustream
accurate I
Producer.
want to be. And then you look at the effective dynamics down here. And when you do that, the K and K prime, if you chose these two, are really independent of each other. You can look for low energy states here or here, and they don't really talk to each other. In fact, in the effective Hamiltonian, if you linearize around momenta at the K point, say this one, up here, you find that, well, it deviates
This is
linearly.
a demonstration
It's complex,
of Ustream Producer.
The matrix Hamiltonian I had in the last page looks like this upper 2x2 block here when linearized about these momenta. And there you have the wave vectors, and this is a Dirac Hamiltonian, the 2 plus 1 dimensional Dirac Hamiltonian. Around the K prime point, it's also like that. Another one, and that you just treat as an independent excitation at this level. And so there's another
2 by 2,
This is a
2 plus 1
demonstration
dimensional
of
Dirac
U-stream
Hamiltonian.
producer.
Right? The Dirac matrices are 2 by 2, the smallest representation in 2 plus 1 dimensions, or 3 space-time dimensions. And so this is it. These are the Hamiltonians. They look a little different. There's some minus signs different, but that's a trivial difference. Actually, they are identical. You can make them identical by, say, in this lower components of the spinner interchanging A and B. That will flip these signs and make it look just like that. So you get 2 identical
This is a
species
demonstration of U-stream producer.
of low energy electrons that behave absolutely relativistically. You would model them with a Dirac equation like this. There's no mass term for them. In fact, they're massless electrons. And there are 2 species here. There's also something I've neglected to mention that's just gone along for the ride so far, and that's that the electron also has spin. And here the spin is just degenerate so far,
This
so
is a
that gives an extra
demonstration
factor
of
two.
U-stream producer.
This way of dividing species is called valleys. The other degeneracy is spins. So 2 valleys, 2 spins, that makes 4 relativistic electrons. So here I've written a relativistic action for them. It's just a Dirac action in 3 space-time dimensions, and there are 4 of them. Now this is a simple model. It's really an independent particle
This is a
picture.
demonstration of
In
U-stream
the field
producer.
theory sense, these electrons are non-interacting. It turns out to be a rather good model for a lot of the properties of graphene. Just forget about interactions and use this field theory. I will argue that's actually wrong, and that it's a mystery as to why this works. And I'll try to offer some ideas about how to solve the mystery, but it is actually an open question
This is a
as to why
demonstration
this
of
should work
U-stream
so well,
producer.
because the interactions that are neglected in getting here aren't all that negligible, actually, at the end of the day. But anyway, this is the model of graphene. So how good is this model? Well, how high can this cone be? Right? How big is the cutoff? Up to about a 1% level of accuracy, where a lot of things come into play, things are neglected. That cutoff can be of the order of an electron volt.
This is a
Even more.
demonstration of U-stream
That's a huge
producer.
energy in condensed matter, an electron volt. Electron volt is 10,000 degrees Kelvin. So in a piece of graphene at room temperature, the thermally excited electrons are way down here. They have no idea that they're anything but relativistic electrons. And so these are relativistic for a very large range of temperature. And this is the one thing that's pretty unique to graphene. If you look at topological insulators, where
This
they
is a
also find
demonstration
relativistic
of U-stream
things,
producer.
there the energy range over which they're relativistic is much, much smaller. It's more like millivolts, not an electron volt. Okay, so that's the model and how you solve it. Now, being a theorist, I can't resist putting in a slide of telling you why I would have known that they were relativistic without even solving that
This
simple
is a
model.
demonstration of
Just by
U-stream
looking at the
producer.
lattice, I would have known immediately that they're going to be relativistic. No group theory, no nothing, just look at the lattice, okay, relativistic. Look at the square lattice, non-relativistic. Right? So how did I know that? Well, this comes from the old days of lattice gauge theory, actually. If I wanted to go the other way, if I was, say, a field theorist interested in this quantum field, this Hamiltonian,
This is a demonstration
the
of U-stream
relativistic
producer.
electron, let's say in 2 dimensions instead of 3 dimensions, like this, and I wanted to put this field theory on a lattice. In other words, define it as degrees of freedom living on a lattice. How would I do that? Well, that's kind of simple. I'd take the 2-dimensional space, I'd approximate it by a lattice. I'd say it's a lattice, not really a continuum. I'd let the fields live on the lattice points, and then I take the derivatives in here
Demonstration of
and
Ustream
approximate them by
producer.
difference operators on that lattice. You know, a derivative is the difference of the field on one lattice site minus a neighbor divided by how far the spacing in between is here, and let's pretend the spacing is 1. And then there are these Dirac matrices, these 2 by 2. Well, this is a Hamiltonian, so it's Dirac's alpha matrices that also appear here. So there's my lattice Hamiltonian. And I'm free to choose the lattice because I'm just constructing something. So let's say I chose the square
Demonstration
lattice.
of Ustream producer.
If I write this Hamiltonian on square lattice and solve its spectrum, actually there's a problem called fermion doubling, in that you get a whole bunch of extraneous species of fermions. It's because the derivative operator as a function of momentum is just something like sine of k. K goes from 0 to 2 pi. Sine of k actually goes through 0 twice, not once. Right? So there are 2 constant functions
This is a
for
demonstration
that
of
derivative
Ustream
operator, not
producer.
just one. And the same thing happens to you here. So this was a big problem in the early days of lattice gauge theory. You get too many fermions. Right? There's more than you bargained for. There's more than just one constant psi that solves this. There's actually probably 4 of them here. So how did they want to deal with this? Well, one way to deal with it is to try to minimize it. So there was a following rather clever observation that's not due to me, it's due to a bunch of lattice gauge
Ustream
theory
producer.
workers, but it is written in old literature from the 1980s. And that's that this matrix in here, alpha, well, it's a Dirac matrix. It squares to 1. It's Hermitian. So it actually is also a unitary matrix. Right? It's a unitary matrix which is its own inverse, but still a unitary matrix. Maybe you could redefine alpha by multiplying the
This is a
size
demonstration of Ustream
by
producer.
matrices. If you multiply all the psi's by a unitary matrix, the psi dagger then by unitary matrix on this side, you'd conjugate this guy. Well, conjugating him will just give you a different representation of the Dirac algebra. That doesn't really do anything. But what if you made the matrices that you redefine psi by depend on the position? Then perhaps you could simplify alpha. The idea is maybe you could diagonalize alpha,
Ustream producer.
like both of the alphas at the same time, by doing something like that, in favor of maybe a position-dependent number in here, and then you could throw away half of them. Right? If you diagonalize them, then you have 2 kinds of fermions that don't talk to each other. You can throw away half, keep the other half, and you've chopped your fermion doubling problem in half. Right? That was the idea. Well, what keeps you from diagonalizing it?
Demonstration of
Well, to
Ustream
figure out whether you
producer.
diagonalize it or not, you should see, in a sense, it's like a lattice gauge field. So what would prevent you from making it trivial, say, is curvature. Right? A gauge field has curvature. What is curvature? It's a product of these things around an elementary cell of the lattice. So if the lattice is square, that product would be like this. Alpha 1 for this direction, alpha 2, alpha 1, alpha 2. Remember, this should really be alpha 1 dagger, but that's the same as alpha 1.
This is
so
a
on.
demonstration
So it's a
of
product like
Ustream
this.
producer.
Well, alpha 1, alpha 2, alpha 1, alpha 2, that product is equal to minus 1. So that means there is curvature. That isn't 1. To have no curvature, it would be 1, but it's minus 1. Minus 1 means there is curvature, but it isn't a matrix. It's just a number. So you could, in principle, by changing phases here, make alpha a diagonal, x-dependent but diagonal matrix.
This is a demonstration of Ustream producer.
Both alpha 1 and alpha 2 at the same time, and then you could actually throw away half the fermions. Okay, that's not what I want to do, but you could do that, and that was called the spin diagonalization technique of reducing fermion doubling. What I want to do is just observe that, okay, this also tells you something else, that the position-dependent alphas you put here would look like a magnetic
This is a
field, actually.
demonstration of
They would
Ustream
look like a
producer.
magnetic field. They have to be complex, and their product around the plaquette would have to be -1. So on a square lattice, if you had a background magnetic field with half of a flux quantum per plaquette, that would give you relativistic fermions. And in fact, that's true in any dimension. Any dimension of square lattice, if you have half a flux quantum in every plaquette of the lattice, that gives you relativistic fermions. You know, just a single
This is a
fermion hopping on
demonstration
that lattice.
of Ustream producer.
So that comes from this old stuff. Well, what about graphene? Well, graphene, there are 6 edges of an elementary plaquette. And just about any way you define alpha matrices for those 6, like you don't project them because they're not quite, you define alpha matrices for directions that aren't exactly just up or down or left and right. Just about any way you define it,
This
the
is a
product
demonstration
around the
of
hexagon is equal to
Ustream
1.
producer.
That means there's no curvature at all in alpha matrices. You can find a lattice gauge transform which just sets alpha is equal to 1. You could throw away all the extra pieces and just consider fermions hopping on the hexagonal lattice, and you know that it has to be a latticization of the Dirac Hamiltonian. So just by looking at the hexagon, you already know that hopping
This is
problem
a
there
demonstration
is
of Ustream producer.
and describes the Dirac Hamiltonian in that dimension, the massless one. Okay. Back to our model. So we found relativistic fermions. What can you do with them? Well, they obey a Dirac equation. There's a Dirac Hamiltonian. Actually, the Dirac operator is a beautiful mathematical operator. It has properties that the Schrodinger operator
of
doesn't
Ustream
have.
producer.
Yes, Schrodinger operator. It also has its own beauty. But the Dirac operator is something really special. For example, there are a set of mathematical theorems called index theorems, which, when you turn on a background magnetic field, say, so think of A as a vector potential that is time independent. So that's just a background magnetic field of some kind, right? The magnetic field is the curl of A.
This is a demonstration of
You don't even have
Ustream
to know what the
producer.
magnetic field is. So in other words, you don't even know what the Dirac equation is. It has an unknown potential. The Thiesiger index theorem tells you how many solutions there are of, say, this 2x2 matrix operator operating on a wave function is 0. It counts those solutions for you. And that, to my mind, is a rather beautiful thing. I know how many solutions there are with a particular
This is a
eigenvalue of the
demonstration
Schrodinger
of
equation
Ustream
when I don't
producer.
even actually know what the Schrodinger equation is. You don't know what the potential here is even. You just know that it has some flux. Well, you need to know one thing about it, and that's the total magnetic flux. So the number of these 0 modes up to, I don't know, 1 or 2 extra ones on an open space is given by the magnetic flux. And that's sort of one nice thing you could see about, the Dirac Hamiltonian, that in a magnetic
This is
field
a
that has a bunch of
demonstration
zero
of
modes.
Ustream
Of course, if it's a
producer.
constant magnetic field, you can find these and you can confirm that this is the right degeneracy of what's called the Landau level. In fact, the whole spectrum is split into Landau levels, and you can find them all explicitly. And there is one that sits right at 0 energy, right at the apex of the Dirac cone, so to speak. And it also, this also actually produces degeneracies. Also, in the neutral ground state of graphene, if these
This
are
is a
0 modes,
demonstration of
magnetic
Ustream
field, they should be
producer.
half-filled. This fact is seen spectacularly in what's called the anomalous quantum Hall effect in graphene. So this anomalous Hall effect was measured sometime shortly after graphene was found in the lab. I guess it's one of the first things you'd think of doing with a material that seemed to have fairly high density of free electrons in it. You might look for quantum Hall physics.
This is a demonstration of
This
Ustream
result, I think, is
Producer.
from the second paper. These are two experimental groups. This is the Manchester one, and this is the Columbia University group centered around Philip Kim. So they published data like this in back-to-back papers in Nature in 2005. And it looks just spectacular. First of all, there were 4 species of fermions, so there's kind of a fourfold degeneracy of everything.
This
That
is a
is seen
demonstration
here
of Ustream
because
Producer.
these steps between plateaus are actually 4 units of the elementary Hall of quanta. You might not be able to see this, but this says 4 e squared over h. So the step is by 4, so there's a fourfold degeneracy. The other thing is, at neutral, charged neutral graphene is right here, sort of right in this riser between 2 steps, right halfway up. And it's
This is
there
a
because
demonstration of Ustream
this
Producer.
Landau level that's sitting right at the apex of the Dirac cones. So neutral graphene has a half-filled Landau level, and that's seen right there beautifully. Yeah?
This is experimental data?
This is experimental data.
Clean, like no noise like this?
Just beautiful.
Okay.
At something like 10 Tesla, the splitting of Landau levels is 450 Kelvin in graphene. So you can actually see this at room temperature.
This is a demonstration of Ustream
Right,
Producer.
and this is cryogenic, as you can. That's why it's so nice. But at room temperature, there's still some quantum Hall physics. It's amazing stuff.
What is the green line?
Which line?
The green line.
This one? This is resistivity. So this one's Hall conductivity of the plateau. This is resistivity. So the neutral state is an insulator, and the other ones have sort of finite resistivity.
This is a
Okay, this was
demonstration
called
of
the anomalous
Ustream
Hall effect,
Producer.
and I think this is what really galvanized the attention of the condensed matter community. They saw this anomalous Hall effect that was so beautiful and so clean, and you actually have the dream of room temperature quantum Hall physics. You might think of making some devices that use the quantum Hall effect that don't have to be cryogenic anymore. But,
But this picture is for the interlayer quantum Hall effect, right?
yes,
This is a
And
demonstration
about the
of
fractional
Ustream
Hall
Producer.
fractional Hall effect has also been seen.
And they estimated the strength of the electron-electron interaction.
That I'll get to. It's strong, but I would say that doesn't really come from the fractional Hall effect. There's some other things that happen with the integer Hall effect that show the Coulomb interaction.
Because there are experiments that pointed that the
This is a
the strength
demonstration of
electron-electron
Ustream
interaction
Producer.
is weak, right?
Some point to the fact that it's weak. There are some that make it look like it's strong. So I'll get to that a little bit.
Okay.
I'll discuss that. In fact, that's going to be important in a few moments. Okay, well, are there Dirac electrons? Well, here's something from the Lanzaro group in Berkeley, a ARPES map.
This is a
of the
demonstration
thermosurface.
of
And
Ustream
there it is,
Producer.
a rather beautiful Dirac cone. Now, the experimenters that I discussed this with, some of them agree it's a beautiful Dirac cone. Some of them still say it's messy. But to my mind, I'm amazed. I mean, it's rather conical. The energy here is actually pretty big. It's 0.8 electron volts. So that's up to our cutoff. Pretty much up to our cutoff, and
This is a
it looks
demonstration
pretty
of
conical to
Ustream
me.
Producer.
It is fuzzed out a little bit here and there, but this actually isn't even a very clean sample. You can see that it's polluted a bit by charged impurities, so the cone isn't exactly centered on zero bias voltage. There has to be some gate voltage put to make the thing neutral. So even in a rather messy, imperfect sample, there's something quite nice. And there's really only
one straightforward
This is a
interpretation of
demonstration
this, and
of
that's that the
Ustream
electrons don't
producer.
interact very much. Because even though the electrons are relativistic, everything else isn't. So if they interacted very much, there would have to be a miracle of some sort to make this conical shape dispersion relation all the way up to an electron hole. Okay, so I'll discuss that a bit more in a moment. This is the dispersion relation in the other direction, perpendicular to the plane.
This is a demonstration
You
of
can see
Ustream
it's,
producer.
a constant. Right, momentum space. Well, the Fourier transform of a delta function is a constant, and you can see it's beautifully constant. So it really is two-dimensional, and it looks like it really is relativistic. And ARPES is probably the best way to measure these things, although ARPES does tend to be polluted a bit by other effects. But I would say it, almost all the other ways you
Demonstration
measure
of
the Faraday
Ustream
surface,
producer.
like magnetic oscillations, introduce things well, I'll talk about it in a moment, but they tend to mess up the relativistic spectrum. Okay, so we found the Dirac equation in condensed matter. So here's a shopping list of what one can do immediately. All right, first of all, Dirac might have unusual electronic properties. So you could run around, and there's tons of semiconductor physics of all kinds.
This is a demonstration
You could try to
of
do
Ustream
again,
producer.
now with Dirac electrons instead of Schrodinger electrons. So that was a cascade of a few thousand research papers over a couple of years, because of course the stuff is easy to make. A micron-sized piece of a material in a nanoscience lab is actually really big and really easy to do experiments with, and so there is a lot of work on it. It has interesting electronic
This is a
properties,
demonstration
so you might
of
want to
Ustream
use
producer.
in electronics. Or nanotechnology, using small pieces of graphene to do this and that, to make devices. Not so nano, but even electronics technology, it's suggested it's an extremely good conductor of electricity. Even not cleaned up, it has about 300 times the conductivity of carbon.
This is a
copper,
demonstration
sorry.
of Ustream
More
producer.
conductive than copper, significantly more conductive. And cleaned up, it comes close to breaking the world record for electron mobility, actually. So it's an extremely good conductor, and it also turns out to be quite a strong material. Remember, it's just one atom thick. So a piece of graphene is like a really, really thin piece of tissue
This is a
paper,
demonstration of Ustream
which is
producer.
strong and not so easy to tear, actually, because of the strong carbon bond. It's somewhat flexible, a little bit stretchy. You can stretch it maybe 20% before it starts to tear. And so you might use it for things. And nowadays, Samsung in particular makes 30-inch sheets of this stuff, and they want to use it for touch screens and foldable computer screens and things like that.
This is a
paper,
demonstration of
there's a
Ustream
whole host of
producer.
applications. So there's a lot of interesting stuff there. But I'm a theorist. I tend to go the other direction when I see practical things. So what would I be interested in there? Well, you have the relativistic electron that you can find just in a tabletop experiment. The other relativistic electrons in the world, you need a particle accelerator to find and study. Here you don't really.
This is a demonstration of Ustream producer.
What's more, there are a whole bunch of phenomena which I remember learning about when I was in graduate school and then quickly forgetting about because they're not really seen in the world and not very relevant. For example, for the Dirac electron, the fluctuations of the velocity are very large. If you look at the variance of the velocity in the wave function of the Dirac electron, it approaches the speed of light. So it's described by this long German word, which means jittery
This is a
motion.
demonstration of Ustream
And then you
Producer.
learn about, and it's a curiosity when you're learning about quantizing the Dirac electron, and then you kind of forget about it because it's not really seen in the real world. And there are other things. There's a Klein Effect tunneling through potential barriers, which I'll talk about in a moment, and all sorts of things. Supercritical atoms you can think of making. The relativistic Schrödinger equation. If you have an atom with too big a charge, Baum states, hydrogen-like Baum states in the atom are
This is a
below
demonstration of
zero
Ustream
energy,
Producer.
and, that has some interesting effects. There's quite a big shopping list, and then in addition to quantum mechanical things, there are also field theoretical issues, which are mostly dynamical. If you introduce interactions, can these interactions do things like drive spontaneous symmetry breaking? I'm thinking here of chiral symmetry breaking, where the massless Dirac electron gets a mass, and things like that. These issues are also kind of interesting. And
This is a
the place
demonstration
where
of
you,
Ustream
really
Producer.
study them, phase transitions, things like that, critical behavior. Okay, well, let me discuss one of them, which is called the Klein Effect, which is kind of important. It's one of the reasons why graphene is such a good conductor. And it's actually, in a sense, works against you if you want to use it for things like a field effect transistor. Why is that? Well, it's because a relativistic
This is a
electron,
demonstration of
when it comes
Ustream
to a potential
Producer.
barrier, passes through with its wave function more or less unsuppressed. That's completely different from a non-relativistic one. When it comes to a potential barrier, its wave function in a forbidden region like this, classically forbidden, has exponential damping, and it comes out very suppressed at the other end. You make a field effect transistor in an ordinary material like this by raising a potential
This is a
barrier to current
demonstration
flow
of
when you
Ustream
want to turn
Producer.
current off. And then lower it again when you want to turn the current on. At least the rough description, that's what a field effect transistor does. Doesn't seem like it's going to work for graphene because in relativistic field theory, the barrier doesn't actually damp the electron. It might scatter it, there might be a diffraction, something like that, but the way its wave function comes out basically the same size as it went in.
This is a demonstration of
This is
Ustream
called the
Producer.
Klein paradox, although it's not really a paradox because it's pretty easy to explain why that happens. It's because, remember, here I've tried to draw the Dirac spectrum. This barrier would look something like this. Right? The potential barrier is just moving up the zero of the energy. So here's the electron spectrum. When the electron is here, it's propagating in a positive energy state on the top part of the Dirac cone. When it comes to the barrier, well,
This is a
there is
demonstration
available a
of
continuous
Ustream Producer.
oscillating state here is just a negative energy state. So you just get a hybridization of positive and negative energy states, and that doesn't do any damping. And then you come out here and it rehybridizes with positive energy states, and there's actually no exponential damping, and maybe some scattering or something like that. And this is basically why, even in relatively impure samples, graphene is extremely conductive. Electrons travel
This is
more or
a
less
demonstration
ballistically
of
because the
Ustream
impurities
Producer.
don't really block their flow. And it's also something that is a bit of a difficulty for technology because it's hard to regulate their flow. It's hard to turn off the conductivity, and that's an open problem. In fact, people dreamt about doing it in various ways. One nice field theoretical way is by doing something that breaks chiral symmetry, introduces a gap
This is
in
a
the fermion
demonstration
spectrum.
of Ustream
Something
Producer.
like what happens in pion physics in the strong interactions. The quarks get mass, pions are those from bosons, and so on. So maybe something like that would happen here, and it doesn't seem to happen. It seems difficult to do, actually. There were various ideas to somehow make graphene more strongly interacting. One of them was stretching it, and that would tend to damp the kinetic energy because that's a tunneling.
This is a
energy
demonstration
between
of
bonds. They
Ustream
stretch
Producer.
longer. That should go down exponentially. Wouldn't change the Coulomb interaction much, so it would make it stronger interacting. It didn't work. There's just no evidence for an energy gap in graphene.
Yeah. How about applying a magnetic field? Does one expect to observe spin splitting?
Things are going to happen in the field. I'll get to that in a moment. Ask me again if you're not happy with what I say in about 5 minutes.
This is a demonstration of Ustream Producer.
And it's an unsolved problem. And it sort of comes to the dynamics of graphene a little bit. So let's talk about dynamics. Let's introduce an interaction. The most important interaction is probably the Coulomb interaction, or the Coulomb interaction of electrons. And that interaction is beautifully strong. So the Coulomb interaction couples something like this. All right, so here's our Dirac action.
This is a demonstration of Ustream Producer.
It's condensed matter physicists call this minimal substitution. We put a gauge field with all derivatives like that. That's going to be the photon field. And then you add the kinetic energy terms for the photon. And that's the Maxwell action. And here I've done it in maybe what looks like a peculiar way. Here's our three-dimensional space-time dimensional world with a graphene sheet. And I've put the Maxwell action in 4 space-time
This is
dimensions.
a demonstration
And of course I
of
do that
Ustream
because,
Producer.
well, the graphene electrons are interacting by the Coulomb interaction. The lines of electric force of the Coulomb interaction are free to spread out outside of the sheet. So at least at the basic level, they should be 4-dimensional. Right? The charge carriers are pinned to the sheet, but the photons can travel outside of the sheet. It's sort of like a brane world, except it's just the electrons that are confined and the photon can go outside. Okay, so it looks something like that.
This is a
And in fact, on
demonstration
the
of Ustream Producer.
next slide is exactly the same, but with the third dimension integrated out in a sense. We've solved the equation of motion for the photon that doesn't couple to anything and plug back in. And as a 3-dimensional theory, this looks, well, it's not local, but it has a source in a local higher dimensional theory, like something like that. Non-local, but still very interesting. As a field theory model, this is quite an interesting
Demonstration
model.
of Ustream Producer.
Reason being is, at the classical level, it's scale invariant. Right? These massless electrons don't have any dimensional parameter. In fact, they only have one parameter, and that's the graphene speed of light, the slope of that cone in the dispersion relation, which is just some number. And it's actually a number which is about a factor of 300 less than the vacuum speed of light. Right? This comes from the material.
This is a demonstration of Ustream
That means
Producer.
that this model is really non-relativistic because the photon should travel with the photon speed of light. Right? 2 different speeds of light in the model. So that messes up the relativistic symmetry. You wonder what you would get after that. Well, things could get messy, and I'd like to argue they don't really. You see this nice conical dispersion relation for graphene, so somehow this non-relativistic nature of the spectrum must resolve itself.
This is a demonstration of Ustream Producer.
This part of the action also has no dimensional parameters. So at the classical level, this is a scale invariant theory. It has no scale. Nothing to set the scale. If you treat the Coulomb interaction perturbatively, I will argue shortly that that is probably nonsense because it's strongly coupled. But if you ignore that subtly and treat it perturbatively, well, it renormalizes in a way that a
This
field
is a
theory usually
demonstration of
renormalizes.
Ustream
And one
Producer.
thing that happens is this speed of light gets a beta function, which makes it depend on energy. And it actually gets bigger at low energy. In fact, it looks something like this. It becomes, well, say, frequency dependent, and looks something like that. Okay?
When you say first speed of light, is it invariant for Lorentz transformation?
Yeah. Well, if you just have the top line That's a Lorentz
This is a
invariant theory.
demonstration of U-stream
In
producer.
fact, if you forget about the gauge fields, it's not just Lorentz invariant, it's conformally invariant. It's a conformal field theory. It has a full conformal group, which is a little bit more powerful than the Lorentz group, actually. It makes a bunch of predictions for you. So that's a scale of Lorentz invariant theory with this speed of light. This one down here is a Lorentz invariant theory with this speed of light, but they then couple to each other at two different speeds of light.
This is a demonstration
you can't
of
have
U-stream
Lorentz invariance
producer.
anymore. But we still have scale invariance in this model at the classical level. And that is broken by quantum effects. And VF becomes frequency dependent, something like this. If it's perturbative. However, graphene probably isn't perturbative. So this line is probably just nonsense. It's the result of a perturbative calculation, and one should understand it differently
This is a
somehow.
demonstration of
And one
U-stream
doesn't really
producer.
understand it differently somehow. I'll give you a few examples, but I would say this is really an incomplete story, which makes it interesting. So why is it strongly coupled? Well, one estimate of the coupling is the fine structure constant. This is indeed the constant that appears when you do perturbative calculations. In fact, notice that in this beta function, it appears right there. Okay, the fine structure constant looks like
Of
this,
U-stream
normally
producer.
with the speed of light here, not the graphene speed of light. It's an estimate of the coupling strength because, well, you can think of it as a ratio of the Coulomb energy of an electron with Compton wavelength lambda to the kinetic energy of an electron with Compton wavelength lambda. Right? The lambda cancels out because of the fact that the electron's massless. And there's the fine structure
This is a
constant.
demonstration of
It
U-stream
has VF here
producer.
instead of C. Well, I could put C here and multiply by this ratio. Then this is a constant I remember off the top of my head. It's 1 over 137. But this ratio is 300. So the fine structure constant here is something like 2.5 instead of 1 over 137. This is much, much more strongly coupled than QED. In fact, the lore is from particle physics, where alpha strong is
This is a
about
demonstration
1.
of U-stream
There, it
producer.
already drives the quantum phase transition, where that phase transition, the quarks get mass, there are pions, Goldstone bosons, and all kinds of non-trivial dynamics. Here, for some reason, it doesn't seem strong enough to do that. There's no evidence that clean graphene has a gap. Again, one of the mysteries. It's not really, it doesn't seem strong enough to drive carbon.
This is a demonstration
But
of
it's strong
U-stream
enough to make
producer.
this calculation complete nonsense. If this term is way bigger than this term, the next term is going to be way bigger yet, and the next one way bigger yet. So there's just no way that can be accurate, that sort of a loop calculation. And to drive the point home, you could try another calculation, which has been done a lot over and over again in the condensed matter literature, and that's the computation of the AC conductivity of neutral graphene. So this is with
This is a
the
demonstration
Fermi level
of
set
U-stream
right
producer.
at the Dirac point. And you do it by simple Feynman diagram calculation using that field theory from the last page. And it's been done up to 2 loops. And this is actually the result with the vacuum speed of light set to infinity, not to C. Well, it's 3 times bigger than VF, so the first approximation is much bigger. You could assume that it's almost infinite and the Coulomb interaction is instantaneous.
This is a
And you get
demonstration
results like
of
this. And
U-stream
here's our
producer.
graphene fine structure constant, and it's multiplied by a pretty big number of order 10. And then this number where there's some cancellation, right? 3 pi is about 10. 11 minus 10 is 1, so it's kind of, there's some cancellation, but it's not enough to make this small. And in fact, you could think of renormalization group improving it with this, which I've already argued is not very sensible. In fact, it's
This is a
running.
demonstration
Coupling has
of
a
Ustream
on-off pole
Producer.
almost immediately as soon as it starts running. And you get a bunch of stuff here which is large and which actually disagrees with experiment. In fact, what experiments see is more or less a constant sigma of omega. This is omega in what's called the high frequency range. Right? So low frequencies, there is a droop peak and all sorts of stuff like structure like that. But if you get up in frequency above, well,
This
the
is a
impurity temperature,
demonstration
something
of
like that,
Ustream Producer.
frequency is much bigger than other scales. It does go flat, and what's seen in experiments is more or less consistent with just this first term. It's not a really easy place to do experiments because it's hard to make graphene exactly neutral. Once there's a density, things can be quite different. So there's a bit of an error bar on this, but it's consistent with actually not having any corrections at all, or very small corrections, and
This is a
certainly not as big as
demonstration
these
of
corrections are.
Ustream Producer.
And these corrections you shouldn't trust anyway because they're bigger than one, and if you go and do 3 loops instead of 2 loops, if you have lots of energy, you'll find some more corrections that are even bigger than these. It's not even a converging series. So this kind of calculation is not very reliable. It has, however, been discussed a lot, and there were some authors who actually found different numbers here that almost cancel. It's sort of interesting and make it artificially small.
This is a
diagram and this
demonstration
diagram
of Ustream
come with
Producer.
different signs, and so there is a sort of tendency to cancel. A nice summary of all this is given in this paper by these authors, actually. There are some nice field theoretical issues of doing the computation about coordinate entities and so on, which have been tossed around in the literature. And I actually don't think the condensed matter physicists actually agree with these guys necessarily. So there is a story to
This
be
is a
told there
demonstration
still.
of Ustream Producer.
Okay, but anyway, the naive, straightforward perturbative calculation doesn't seem to be very accurate. It doesn't look like the way to go here. Can one improve it? Can you do something better? Well, one systematic way to do something which I believe is better is to do something like the 1/n expansion.
This is a demonstration
try to
of
do that.
Ustream Producer.
The 1/n expansion. How do you do that? Well, there were 4 species of relativistic fermions. Let's just pretend they're n. And n is a large number, and we'll try and do an asymptotic expansion of things in 1/n. And then at the end of the day, put n equals 4. So our coupling constant, in a sense, is a quarter. Well, that's way better than the Coulomb
This
interaction
is a
coupling
demonstration
constant.
of Ustream
Still not really
Producer.
small, right? 25% error in the leading order and so on. But maybe there's some hope. One thing that happens that actually explains something here in large n is if you make the effective Coulomb interaction. So in this approximation, I have to take into account screening from electrons, how it affects the Coulomb interaction or the
This is a
Maxwell
demonstration
action.
of Ustream
And you can do
Producer.
that just by doing a Feynman integral, and you find something that looks like this. It's a lot like that, in fact adds to it. So if you look at the dynamics of the photon, they're now governed by this action. If n is large, you could ignore the second one. In fact, if you look at it, it isn't that large. It might be a factor of 5 to 10 bigger, but okay,
This is
ignore
a
it anyway.
demonstration of
Then
Ustream
notice what
Producer.
happens. This is the same as this, except the speed of light is the graphene speed of light. So now the effect of photon-mediated interaction actually has the graphene speed of light. Physically, you can think of it this way. The photon has now become screening-dominated. So the tree-level photon that floated around in 4 dimensions is no longer relevant,
There's a kind of an exciton that
This is a
travels,
demonstration
or
of
an
Ustream
exciton
producer.
resonance that travels along the material that actually takes over for what the photon does. Is a stronger, is the more important interaction, and it actually is Lorentz invariant.
Just one comment. In condensed matter language, large and limited means that you are doing in mean field theory. Is like this.
It's a sort of a mean field theory. Yeah,
This
it's
is
not
a
that far off.
demonstration of
It's,
Ustream producer.
Not exactly, because it's actually more like Hartree-Fock. In fact, making something screening dominated is taking the Hartree-Fock approximation seriously, and then the corrections are bigger than the leading order in that approximation. So it's more like Hartree-Fock than mean field theory. The other thing is, well, this is a relativistic field theory, so now our Dirac cone has a right to be a cone.
This is a
In fact, it could still
demonstration
be
of
strongly
Ustream
coupled,
producer.
because if I forget about this, I just have this and massless electrons. That's a conformal field theory. It has scale invariance, and actually there isn't a beta function for anything. The scale invariance survives at the quantum level. Well, that's known up to 2 loops in perturbation theory. It's not really a theorem. And so this beautiful cone structure, the Dirac cone, in that field theory would be exact.
This is a demonstration of
Even
Ustream
if
producer.
the coupling is strong, actually. Then it isn't really a Fermi surface, because Fermi surface is a single electron notion. Right? And if the coupling is strong, you don't know what a single electron is anymore. But what ARPES really maps is the singularity in the current-current correlator, and that's the thing that's conical. Right? And that will still be there in a strongly interacting material. And so that actually looks pretty good.
This is a
So if
demonstration
one took
of
the large
Ustream
expansion
producer.
seriously, we're in pretty good shape. And then perhaps treat this as a perturbation. Well, you have to at some level. And actually, when you do that, you do get a beta function again. You can think of it as a beta function for this term, actually, and it runs to 0 rather slowly in the infrared. So it's actually stable in this 1/n expansion, the conformal fixed one. And another way to see that is if you go back
This
to
is a
the
demonstration
go
of
to
Ustream
this theory with
producer.
relativistic fermions, the perturbation of the velocity of the Dirac operator is actually an irrelevant operator. It's marginal at the tree level and becomes marginally irrelevant when you start to renormalize. So large N actually gives you a kind of a starting point, which is a conformal field theory, and where at least the relativistic looking things are there. And in fact, you can do more. I had one of my graduate students actually did this calculation.
This is a demonstration of Ustream
You can
producer.
go back to the AC conductivity, which we calculated before a couple of pages ago. It looked like that, and do it in the 1/n expansion instead. That basically takes this photon propagator here and resums it like Hartree-Fock. With this bubble, sorry for the poor quality of the drawing, this is actually this bubble. So it resums them all and then uses the sum of all these in this place. So I think that's what condensed matter physicists would call Hartree-Fock,
This is a
actually.
demonstration
But in
of
the
Ustream
1/n,
producer.
it's a systematic expansion, and it gives you an expansion of the quantity in 1/n. So here it is. So the leading term has n/4, which goes to the graphene thing when you put n equals 4. And then it's multiplied by something with a 1/n correction. And there, these two diagrams, actually they do almost cancel if you calculate what they are. So this thing, 92/9 pi squared minus 1, is actually a small number, 0.045.
This is a
So
demonstration
not
of
only is
Ustream
1/n
producer.
helping you here, well, when n is 4, it doesn't help you much, right? But this turns out to be a small number.
What about the next one?
Pardon?
What about the next one? The next one?
Okay, that's the golden question. That's the golden question, and you can ask it this way. In fact, if anyone has the energy to do 3 loops, it should be an answerable question. So, is the
convergence of the series
This is a
estimated by the
demonstration of
size of
U-stream
one of
producer.
these times this? Or is it estimated by the combination of these times this? That's the golden question. The answer, I do not know. Okay? If it's the combination of the things, then we're in pretty good shape. It's converging quickly. If it's just the magnitude, then, well, it's not as bad as a coupling constant expansion, which is diverging, but it is not that good because this is 1, this is the order 1,
This
so
is
the
a
corrective is the
demonstration
same
of
size as the
U-stream
leading
producer.
order. And it takes computing the next order, I believe, to resolve it. At the next order, there will be some effect of a running coupling because the beta function for the tree-level photon will cut in. So it becomes actually a very interesting calculation in a number of ways. But nobody has done it, and I don't know of anyone who's actually trying to do it.
Sometimes from the look, the same reasoning you have in TCD, you would expect something of the other 0.25
This is a
squared.
demonstration of U-stream producer.
Do the experiments get that well? Or
The experiment would agree with this rather well. What they see is actually, they're not that accurate, but what they basically see is E squared over 4H. They basically see the free fermion result. And here we see in a strongly coupled, very strongly coupled theory, screens down the interaction to where, well, it's sort of the free fermion result. It's consistent with experiment, actually.
This is a demonstration of U-stream producer.
But there is this theoretical question of, is this really converging? I mean, that would be an important result. And there aren't many three-loop calculations that I can tell you would be important. Okay, well, I'm going over time here, so I'm going to go quickly through this. There's a bunch of experimental work on whether VF really runs. I might want to claim that, okay, maybe
This is a
graphene finds a way to
demonstration
be a
of
conformal
U-stream
field.
producer.
Like it seems to be in the infinite n limit, perturbatively 1 over n. And that would mean that nothing should run. That VF should be at a fixed point for a lot of this energy regime where you see the Dirac cone. Well, experimentalists have gotten interested in this and they've looked for the running VF. This is the Manchester group. So they claim to see it.
This is a demonstration of U-stream producer.
And the condensed matter community actually views their results as reliable. They think they're reliable. They think they're reliable because they're magnetic resonance measurements. They basically measure the cyclotron frequency as a function of density, and then somehow the cyclotron frequency is related to this VF parameter. So they extract it as a function of density, and then they kind of trade that around, and they claim it runs. I would criticize it on just one ground, and that's that they use a magnetic field at a density that actually breaks all the symmetries that protect the masslessness of the Dirac electron. The Dirac electron is free to have a mass gap once you introduce a magnetic field and a density.
But the effect should be small, right?
Well, I don't know. It's not really calculable in perturbation theory, but they claim they
This is a
see it.
demonstration
This
of
is the
U-stream
Columbia group.
producer.
They see really strange results. What they do is they use scanning and tunneling electron microscopy. So they see a Fermi velocity, which does, they measure it as both a function of frequency and density. So as a function of density, it changes. As a function of frequency, it seems to be a constant. It's absolutely bizarre. I know of no theoretical explanation
This is
of
a
that.
demonstration of
If you
U-stream
have one-
producer.
Well, maybe keep it a secret.
You're
Publish it.
You're basically saying that all the usual strategies we use to compute things in 3D are completely wrong in this case.
Okay.
So if you do perturbation theory using
Yeah,
Einstein thing, just won't work.
yeah, I mean, it's a diverging series. Quickly, rapidly diverging. Okay, so these guys have bizarre results.
And they use STM.
This is a
And my
demonstration
favorite one
of
is the
Ustream
Landauer group in
producer.
Berkeley, who uses ARPES. So ARPES is messier a little bit than those other techniques, but they don't need a magnetic field, they don't need a density. They could really try and tune the density to 0 and measure the Dirac cone directly. And the red line, the solid red line, is what they see. And the dotted line beside it is a straight line. And they try to argue they see deviations. And
This
they
is
even
a
try to argue that the
demonstration of
deviations are
Ustream
down here,
producer.
where I don't see any deviation. And the deviations here, I think in other papers they say the deviations are here. But look, this is their cutoff. It's the spectrum is supposed to start curving there. Right? This is already an electron volt in energy. So I would say there's a pretty big space here where they see nothing but a perfect cone. Yeah.
This is a demonstration of Ustream producer.
And they've actually adjusted this dotted line to kind of maximize deviation down here at as low an energy as possible. But if you can see if you do it on the other side, the deviation would be up above the cutoff already. So, to my mind, they're seeing a conformal field theory.
The change in the shape of the cone is due to the electron-electron interaction.
Yeah, that's what they claim.
So, here, as far as I realize,
This is
you
a
are close to the
demonstration
zero
of
the
Ustream
cone
producer.
of the cone. There exist some predictions for the one-hot singularities if there is one change due to the electron-electron interaction.
Yeah, there are, although these are usually modeled in the continuum, so the Van Hook singularities are very far away. This is a very low energy.
Because as far as I realize it, your theory is relatively close to the zero
This is a
after this.
demonstration
Yeah.
of
And when
Ustream
you talk
producer.
graphene, you can achieve the one-hot singularities,
Yeah.
so you can change the electronic properties.
Yeah.
For example, there are experimental results that suggest that graphene can be superconductor.
Yeah, at some high density.
Yeah, yeah.
Really doping, yeah, right. But not near zero doping.
Yes.
And this is only, I'm discussing actually absolutely zero doping here.
Yeah.
This
If
is
you
a
dope it, of
demonstration
course,
of Ustream producer.
density is a dimensional parameter and it ruins my conformal symmetry. So my claim that graphene wants to be conformally symmetric applies only to the zero density case.
Right.
But to me, that's an experimental test, and it looks pretty conical over a big range of energy again. Okay, so what else can one do? Well, I've gone way over time here. There is some direct evidence for strong interactions.
demonstration
in that
of
these Hall
Ustream
states
producer.
are split if you go to cleaner samples and bigger electric fields. So this degeneracy of 4 is really split into 4 steps. The steps are incompressible, the plateaus are incompressible states, so there's an energy gap there. And the gap is commensurate with the strength of the Coulomb interaction, estimated as a strong interaction. So the gap is way bigger than you could ever account for by a weak interaction.
This
And
is
so
a
that's taken as
demonstration of
direct
Ustream
evidence of the
producer.
strength. The fact that the electron, the Coulomb interaction is strong. So that's one bit of evidence that it is really strong, and perhaps if this is a CFT, it's a non-trivial one.
Is this an effect of the low temperature?
This is low temperature.
What made people observe this?
They went to
What's the
higher
difference between
fields.
this experiment and the other one?
The difference between
Yeah.
higher fields, cleaner
This is a
samples,
demonstration
lower
of
temperature.
Ustream producer.
Right, so just more stable. In fact, they only really saw these, I believe, in suspended samples at first. Although the best results are actually due to the Columbia group, who basically see the whole, up to the 20th, something like the 20th step, completely resolved into integer steps. So they see this fourfold degeneracy completely broken.
This is a demonstration
And they
of
attribute
Ustream
it to
producer.
spontaneous symmetry breaking. It's way too big, the gaps are way too big to be due to residual lattice effects and kind of explicit symmetry breaking like Zeeman interaction. And it appears like they come from a strong Coulomb interaction. They're consistent with the scale of the Coulomb interaction. Just a naive estimate of it. In fact, that's here. This is energy in
This
degrees
is a
Kelvin.
demonstration
I
of
think
Ustream
this line
producer.
is the Coulomb interaction, and this is the Landau level splitting as a function of V in Tesla. And these things down here are residual lattice effects in the Zeeman interaction, and the splitting is actually consistent with this one. It's about that size, almost the same size as the Landau level splitting itself.
Is this a room temperature experiment?
No, this is cryogenic.
It's cryogenic.
Yeah.
This is a demonstration of
So
Ustream
I've run out
producer.
of time, but let me just give you a very theoretical bit of evidence for my conformal field theory idea. And that's that I can do a kind of a string theory holographic construction of graphene. And that construction assumes it's a conformal field theory, and it takes a strong coupling limit. And the theory is not exactly graphene. Actually, it is a two-dimensional relativistic electron gas.
This is a
So it's like the
demonstration
low
of
energy limit of
Ustream
graphene.
producer.
The interactions are a little bit different from the photon-mediated interaction. It's because of their interactions more like a non-abelian gauge theory in a certain limit. The limit is one where you just sum planar Feynman diagrams, you throw away all the rest, and the photon self-correlates in a certain way. So it's a different kind of interaction, but one can go to the strong interaction
This is
limit
a
there
demonstration
and
of
study
Ustream
the
producer.
perturbation theory around strong interactions.
And everybody has the same velocity.
Pardon?
Everybody has the same velocity. There's only
Everybody has the same velocity. So I'm assuming graphene has found a way to be a CFT. And in a sense, the part of the interaction I'm using is complementary to the one that's used in the large N expansion. It's different from Hartree 5. And there one can also compute some things, and then kind of a miracle happens. If I go back and
This is a
compute
demonstration of
AC conductivity, I get a
Ustream
number.
producer.
It doesn't look like this, but actually it's within about 20% of this. So going from zero coupling to infinite coupling, that AC conductivity has only changed by about 20%. It seems rather insensitive to the strength of the coupling. And actually in this business one can compute a bunch of other things that come, I won't tell you any details, come more or less
This
for
is a
free.
demonstration
But one
of
thing that'd be
Ustream
really interesting
producer.
to measure is the diamagnetic moment of graphene. I think that's rather easy to do, and probably has been done. But one thing to look for, the conformal field theory idea, would tell you it should scale like the square root of B. The condensed matter communities, there's many confusing papers about this because they try and compute the diamagnetic moment, which is a derivative of this by B and then setting B to 0, that diverges.
This is a
Forget about
demonstration
the
of
moment,
Ustream
the
producer.
magnetic moment, just calculate the susceptibility, I should say, just calculate the diamagnetic moment, this thing. It would be really interesting to even see if it scales like the square root of B. Also, this strongly interacting model, it predicts a diamagnetic moment which is somewhat larger than just the free field limit, like about a factor of 5
This
larger.
is a demonstration of Ustream
Factor
producer.
of 5, I don't know. That might be visible. It's not exactly a smoking gun of anything, a factor of 5, because there are lots of things that could account for it. But it would be interesting. I think that would be very interesting. And there are a bunch of other things one can do with playing around with these models. But probably the most interesting tests are just for the scaling of conformal invariance, like the square root of B. Okay, so finally conclusions. So I've told you that graphene has
This is a
massless
demonstration
relativistic
of
electrons.
Ustream Producer.
There's some interesting consequences of that, the nice material properties, the sort of nice theoretical playground, or relativistic field theory playground. The Coulomb interaction is quite interesting in graphene because it seems to be strong, and one should try to understand its effects a little better than are currently understood. There's the obvious question, how do you get Dirac cone when you have strong non-relativistic electrons? Or strong non-relativistic interactions. And one of them is a hypothesis that somehow graphene finds a way to be a conformal field theory. And then I just mentioned the D-brain construction of graphene, showed you 3 computations of AC conductivity, and I hope I managed to convince you that those computations are interesting. Thank you.
Ustream Producer.
Okay, so are there any further questions?
I'm going back to my question.
Yes.
Could that four-fold splitting be fully observed in a tunneling experiment through a single barrier, for instance?
The fourfold splitting, well, that's in a magnetic field,
Yes.
right? Tunneling experiment.
This is a demonstration of Ustream
I'm
Producer.
not aware of that. It's basically seen by splitting of the Hall steps. So as a Hall effect. It's been studied a lot because there's quite a bit of interesting physics just in the charge-neutral splitting. It's an insulator, there's some metallic phase in there, metal insulator transition. There's lots of stuff that happens there. It's been a bit controversial because these experiments seem to be difficult to
This is a
reproduce.
demonstration of Ustream Producer.
In fact, in some of them, even in the same sample, you heat it up and cool it down and it behaves differently. Charge neutral is a difficult place to be because of charged impurities, or any impurities tend to make what's called a puddling of the charge. So that even if the material is overall neutral, there are sort of puddles of electrons and holes here and there, and locally it's not charge neutral. So experimentally
This
it's
is
a difficult place to
of
work.
Ustream Producer.
It's improved quite a bit recently because they learned how to put graphene on a boron nitride substrate. Boron nitride is the same hexagonal lattice as graphene, except it's alternating boron nitrogen, and so it breaks some of the symmetry. And they were originally hoping that they could induce chiral symmetry breaking in graphene by doing this, and that never worked. I could see no one ever made that work, but they discovered that boron nitride is a very nice
This is a
substrate.
demonstration of
Once you get a
Ustream
piece
Producer.
of graphene sitting on it, it tends to not have the wrinkles, and it tends to be really clean. The charged impurities are reduced by something like a factor of 10,000 in density. It's really much, much cleaner. And so this last picture I showed you where they see all these Hall levels, that's with graphene on boron nitride. And it should be possible with that technique to get actually much better charge neutral results. I do expect
This is a demonstration of
AC
Ustream
conductivity at the
Producer.
charge neutral point measurement to appear pretty soon. That's way better than previous ones. And maybe will tell us what it actually should be with some precision. For example, one could compare this 1/n expansion with it. That would be interesting.
Could one try to make intuition analogy between optical interferencing barriers?
You mean another velocity?
Yes. From what you explained,
This is a
those
demonstration
electrons, they
of
do not
Ustream
follow the
Producer.
phase like we
Yeah,
do.
what happens here is when you have two speeds of light, the renormalization group running tends to make them run together. And the perturbative running makes the lower one run up to the higher one. The higher one kind of just sits there. The higher one is the speed of the photon in the vacuum. And definitely the electron doesn't have that speed in graphene. You can just see it from the slope of the ARPES spectrum. It's
This is
much
a
closer to
demonstration
the
of Ustream
naive
producer.
estimate, the C over 300. One speculation, if you like doing a two-loop calculation, go to 1 over n, calculate the beta function, leading term and next to leading term. Maybe there's another fixed point. Maybe it stops before it gets to the speed of light at another number.
Like 1 over 300.
Well, 1 over 300 is where it starts.
This is a
But
demonstration
what's
of
seen is actually
Ustream
not much
producer.
more than that. So maybe, once you get 2 terms, there's another 0 of the beta function. Just the speculation,
But I
but
was going to ask, but in some sense, the theory looks like it's strongly coupled, but in some other sense, the classical computation that we did on the conductivity and things like that, it's really weakly coupled, right? In fact, the corrections, they don't matter. At least
that's right. In 1 over n, it didn't matter.
I mean,
This
you
is
don't
a
see much
demonstration
deviation
of
from the
Ustream
classical
producer.
That's right. But that part, even in the holographic construction, the string theory construction where the coupling is infinite, it didn't change much. So that just happens to be something that's not that sensitive to strong coupling, probably.
It's just assuming that certain hollow point already takes care of it.
Well, it's just not very sensitive. I think that was seen in the quark gluon plasma business holographically.
This is a
There's
demonstration
just lots
of
and lots
Ustream
properties that
producer.
aren't that dependent on the strength of the coupling constant. And then a few that were dramatically dependent on it. And here I haven't really found the dramatically dependent things yet.
Any extra questions? No, if not, let's take Professor Semenoff again.
This is a demonstration of Ustream producer.